Chapter 4, Motion. This lecture will help you understand motion, speed, and velocity. What is motion? Motion is just a change in position. Speed is a measure of motion. Aristotle was a Greek philosopher who lived between 384 and 322 BC. When Aristotle tried to find the causes of motion, he said that some forms of motion were natural. Rocks fall toward the ground because the ground is a natural place for the rocks to be. Objects rise into the air when they are heated because the sun is hot, and so it is natural for heat to rise. Aristotle classified other forms of motion as violent because they were not natural to his way of thinking. For example, shooting an arrow through space produced violent motion, since the arrow's natural tendency was to fall straight down toward Earth. Natural motion, motion that is straight up or straight down. Violent motion is imposed motion resulting from an external push or a pull. Aristotle also said that objects move only when they are being pushed. Push a block across the table, and when you stop pushing it, it stops moving. Later, we will see that Aristotle did not understand the concept of friction. Speed is described as the distance covered per amount of travel time. If you travel 50 miles in 2 hours, your speed is 25 miles per hour. Speed represents how fast something is moving, yet it does not indicate the direction in which it is traveling. Distance travel is different than displacement. When traveling from A to B, any path may be followed, and the total distance traveled can be quite large. Displacement is the net change of position of an object. It is represented by a straight line from the initial position to the final position. It is the shortest distance between 2 points. Displacement is also a vector because it has both magnitude and direction. Starting from A and ending at B is different than starting at B and ending at A. The displacement is signified as delta S. It is the straight line distance from A to B. The triangle symbol in front of the S is the Greek letter delta. In physics, it is a symbol that just means change in. So S is position and delta S means change in position. Speed is the displacement divided by the travel time. It is symbolized by the letter V with a subscript AVG. We define the Greek letter delta to mean change in. We can expand the meaning of delta as follows. For any variable S, delta S is defined as S final, our final position, minus S initial, the initial position. Delta S is positive if the final position is larger than the initial position, and negative if the final position is less than the initial position. Our definition of delta is always final minus initial, regardless of the meaning of S, which can be position, velocity, force, or even temperature. In physics, the direction of motion is usually given as shown. Motion to the right or east is given as positive, and the motion to the left or west is given as negative. Motion up or north is positive, and motion to the south or down is negative. The number line shows 4 positions, A, B, C, and D. Let's imagine a bee flying from A to B, then to C, and finally to D. Let's define the motion from A to B, B to C, and C to D. For the motion A to B, the initial position at A is 6. The final position is 10. The displacement is to the right and is positive in our convention. For the motion B to C, the initial position at B is 10. The final position is 8. The displacement is to the left and is negative in our convention. For the motion C to D, the initial position at C is 8. The final position is 1. The displacement is to the left and is negative in our convention. Remember, the delta notation can be used for position, speed, acceleration, forces, and almost any quantity. The notation is always final minus initial. Instantaneous speed is speed at any instant of time. Your speedometer gives instantaneous speed, not average speed. During a trip from Nashua to Concord, your instantaneous speed may vary from 10 miles an hour to 80 miles an hour. But your average speed is a single number, say 50 miles per hour, the total distance divided by the total time. Velocity is the rate of motion in a direction. We must have the direction component to specify velocity, otherwise it is just a speed. A car rounding a corner may have constant speed, but since the direction is changing, the velocity is changing. Now we look at motion diagrams. An easy way to study motion is to make a video of a moving object. A video camera takes images at a fixed rate, typically 30 every second. Each separate image is called a frame. Shown are 4 frames from a video of a car going past. The car is in a different position in each frame. Suppose we edit the video by layering the frames on top of each other, creating the composite image shown below. This edited image, showing an object's position at several equally spaced instants of time, is called a motion diagram. The time between frames is constant, so the positions of the car mark equal intervals of time. The velocity, distance, and time for a car traveling at a constant velocity of 10 meters per second to the right is shown in 1-second intervals. The motion diagram shows the direction of motion, the speed at each time interval, and the position at each time interval. The average speed in driving 30 kilometers in 1 hour is the same average speed as driving A, 30 kilometers in 1/2 hour, 30 kilometers in 2 hours, 60 kilometers in 1/2 hour, or 60 kilometers in 2 hours. The answer is D, 60 kilometers in 2 hours. The displacement of 30 kilometers is divided by 1 hour, so the average speed is 30 kilometers per hour. Now we'll do each of these in turn, A through D. 30 kilometers divided by half an hour is 60 kilometers per hour. 30 kilometers divided by 2 hours is 15 kilometers per hour. 60 kilometers is divided by half an hour is 120 kilometers per hour. And 60 kilometers divided by 2 hours is our 30 kilometers per hour. Find the average speed of a car that travels 160 kilometers in 2 hours. First step is to write down what we know. The displacement is 160 kilometers and the time is 2 hours. We're looking for the average velocity. The basic equation is our displacement equation. Delta S equals V average times delta T. The basic equation must be rearranged to obtain the working equation. V average is delta S divided by delta T. We now substitute the known values, which allows us to calculate that the average speed is 80 kilometers per hour. Here's a velocity example. Find the velocity of a plane that travels 600 kilometers due north in 3 hours and 15 minutes. Keep in mind that the velocity includes direction, so a direction must be included in the answer. First step is to write down what we know. The displacement is 600 kilometers and the time is 3.25 hours. We are looking for the average velocity. The basic equation is our displacement equation. the basic equation to obtain the working equation. Substituting the known values allows us to calculate the average velocity of 185 kilometers per hour. But since we are looking for a velocity, we must have a direction. Velocity is always in the same direction as the displacement. Since the motion is due north, the velocity is 185 kilometers per hour due north. Motion is relative. Everything is always moving, so motion is relative. At this moment, your speed relative to the sun is about 100,000 kilometers per hour. When we say a space shuttle travels at 30,000 kilometers per hour, we mean relative to the Earth. It's not a good idea if you get stopped by the police who ask if you know how fast you are going to say 30,000 kilometers per hour. They won't appreciate the humor. A more practical example of relative motion is an airplane flying into a headwind or in a crosswind will have a different ground speed and direction than a plane flying in no wind. The airplane speed is measured with respect to the wind, not the ground. This is why flights flying west take longer than flights flying east. The jet stream flows west to east. A plane flying west is flying into the wind and has a lower ground speed than a plane flying east with the wind. In the last lecture, we reviewed the trigonometric identities. Here they are again. We also introduced vector notation. The r sub x and r sub y vectors are the components of vector r in the x and y directions. The I and j with the hats are the unit vectors in the x and y directions, respectively. So r sub x and r sub y are magnitudes of the rx and ry vectors. The magnitude of the r vector is the square root of the sum of the squares of the x and y components. A plane is flying due north, which is at 90 degrees as a standard angle, at 265 kilometers per hour relative to the wind, and encounters a wind from the east, which is 180 degrees, at 55 kilometers per hour. What is the plane's velocity with respect to the ground? The data are the wind speed in the x direction and the plane's motion in the y direction. The x and y components are minus 55 kilometers per hour and 265 kilometers per hour. The basic equations and the working equations are the same. The magnitude of the vector and the helper angle of the motion. Substituting what we know, we find the magnitude as 271 kilometers per hour. Using your calculator and the inverse tangent function, the helper angle is found to be 78.3 degrees. Make sure you know how to use the inverse tangent function on your calculator. If you do not, you need to ask. The helper angle is 78.3 degrees. But this is the angle between the resultant vector and the x-axis. But we want the angle counterclockwise from east, the standard angle. From the figure, the resultant vector is in the second quadrant. The standard angle is the 180 degrees minus the helper angle, which gives a standard angle of 101.7 degrees. The velocity of the plane relative to the ground is 271 kilometers per hour at 101.7 degrees. Here's a second example. A plane is flying northwest, 135 degrees, at 315 kilometers per hour, and it encounters a wind from 30 degrees south of west. at 65 kilometers per hour. What is the plane's velocity with respect to the ground? We must proceed by finding the x and y components of both the plane's and the wind's velocity. The basic equations and the working equations are the same. The components of a vector and the magnitude of the vector and the helper angle of the motion. Let's look at the x and y components of the plane. The x and y components of the plane are shown on the figure. The x component is pointing west, so it must be negative. Using the helper angle, alpha, which is 45 degrees, the x component is 315 kilometers per hour, times the cosine of 45 degrees, which gives minus 223 kilometers per hour. The y component points north and is positive and is equal to 350 kilometers per hour times the sine of 45 degrees, which gives 223 kilometers per hour. And for the wind direction is east and north. The angle is 30 degrees. The x component is 65 kilometers per hour times the cosine of 30 degrees are 56.3 kilometers per hour. The y component is 65 kilometers per hour times the sine of 30 degrees are 32.5 kilometers per hour. Both components are positive. The direction of motion of the plane in the crosswind is the vector sum of the two vectors, wind and plane motion. Add the x and y components individually. The x component of the resultant vector is minus 165 kilometers per hour. The y component of the resultant vector is 256 kilometers per hour. Note that the x is negative and y is positive, so we are in the second quadrant. The magnitude of the resultant vector is the square root of the sum of the squares of the x and y components, or 306 kilometers per hour. The helper angle is found to be 56.9 degrees. Since we are in the second quadrant, the standard angle is 180 degrees minus the helper angle, which is equal to 123.1 degrees. The velocity of the plane relative to the ground is 306 kilometers per hour at 123.1 degrees. This is an example of how the velocity of a boat and the velocity of a river current are combined so the resultant velocity is directed toward the desired location. The boat captain must compensate for the current and steer slightly up current to head straight towards the dock. A hungry bee sees a flower in a 5 meter per second breeze. How fast and in what direction should the bee fly in order to hover above the flower? It should fly toward the flower, then at 5 meters per second into the breeze. It should fly with the breeze at 5 meters per second away from the flower. The bee will not be able to fly in a 5 meter per second breeze. The bee will not be able to reach the flower. And the answer is it should fly toward the flower, then at 5 meters per second into the breeze. When just above the flower, it should fly at 5 meters per second in order to hover at rest. This is why bees grip onto a flower to prevent from being blown off.